Okay, so when it comes to using Hess's law in order to determine the delta H of reaction using these heated enthalpies, you have to understand first off what we're talking about when we talk about the delta H of formation. And so whenever I talk about delta H of formation, I am basically saying how much energy is being released or how much energy is being absorbed whenever this stuff is being created. And so the great thing about this is if we are talking about the enthalpy of formation, when it comes to things that exist in the same exact form they always exist in. What I mean by that is if you have something like a diatomic gas, if you have diatomic gas or something like chlorine or O2, that is always going to exist in the form of the diatomic gas. You as a person did nothing to make that happen. You as a person did absolutely nothing to make oxygen oxygen. It's just the way it has always occurred. And so the delta H for formation, or the amount of energy required to make O2 in the form of O2, is zero because there is no energy required to make that happen because it's just the way it already exists. But if we kind of talk about the same idea when we discuss metals, and so metals that typically exist as solids are not going to require any energy to be formed into sodium solid because it's already in that form. And so when we talk about these delta HFs of, again, what they call the standard states, or the way that these things will already exist in nature, the way they always exist, the delta HF for those are always going to be zero. But if you take something like sodium solid and you add it to chlorine or CO2 gas, you will form sodium chloride. But in order for that reaction to occur, some energies has to either go into that system or be released from that system in order for these things to actually change. And so and again, that's going to come up more in the next couple chapters here. And so in this situation, the formation of sodium chloride is an exothermic reaction, meaning the fact that when you take sodium metal and you combine it with chlorine gas, it's going to release 411 kilojoules of energy per mole of sodium chloride in order for that sodium chloride to be produced. And so, same kind of idea is going to be translated into whenever you take CO2. And so CO2 exists as a diatomic gas in nature. That's how it always exists. And so the delta HF for your CO2 is going to be 0 kilojoules per mole. But Cl, or a chlorine ion by itself, needs to have some way of being formed because it doesn't exist that way by itself. And so kind of think about the idea is if you have a stick in your hand, you have to put energy into that stick in order to break it. You can't just stare at it and it's going to break on its own. And so in order to have CO2, again, two atoms that are combined, you have to have something in order to break those two atoms apart. I mean, the fact you have to go in there and literally go, hi-ya, and chop those atoms and so they kind of separate. Meaning the fact that, again, it's going to have some energy kind of being released or absorbed when this reaction kind of goes and occurs. And so this, again, is also going to have an electron being added into this in order for this whole idea to occur. And so the whole thing I'm trying to illustrate here is if you have something in a standard state, it's going to have a delta HF of 0. If you have something being formed that is not in the way that it normally occurs in nature, like sodium chloride or chlorine all by itself, then you're going to have to either put some energy into the system to make it happen, or you're going to have to, again, release some energy in order for this reaction to occur. And so, say that we have a problem that is talking about nitrogen monoxide gas is added to oxygen gas to produce nitrogen dioxide gas. And so here I want you to calculate the standard heat of formation of the reaction. And so one thing I have to make clear here is I do not expect you to memorize any of these values. These values will either have to be given to you in the problem or you're going to be solving for one of these. And so if we have nitrogen monoxide gas, first thing you have to work out is, let's do a different color here. And so nitrogen monoxide gas, and we are adding this to oxygen gas to produce nitrogen dioxide gas. And so, first thing you should always do when you have a chemical reaction is make sure it is balanced. In this situation, it is not. But if we take a 2 here and a 2 there, now we have 2 nitrogen monoxides plus an O2 will produce 2 nitrogen dioxides. And so delta H's F's, well, they can be found in most general chemistry books. But I will tell you this, the delta H of formation in the standard states of your NO is going to be 90.4 kilojoules per mole. And the delta HF of your NO2 is going to be 33.85 kilojoules per mole. So one thing you have to understand about these kilojoules per mole is the way I wrote it out is I'm telling you that this is 90.4 kilojoules per 1 mole of nitrogen monoxide. This is 33.85 kilojoules per 1 mole of the nitrogen dioxide. One other thing you have to kind of notice here is I gave you information about nitrogen monoxide and nitrogen dioxide. And the one reason why I kind of left it out here is because I wanted to bring it up for this problem is I do not give you a delta H of your O2 because the delta H of oxygen as a gas, a diatomic gas, the way it always occurs in nature is going to be 0. And so your delta HF of your O2 is equal to 0 kilojoules per mole because you do not need to do anything. You don't need to release energy, you don't need to absorb energy for O2 to be O2 because it's already in that form. And so, next thing you have to do is just take this balanced equation and plug these values into where you need to. And so the delta H of your reaction, as I've kind of mentioned in class, but like in the past, you have to understand that your delta is always going to be reaction, is always going to be your final minus initial, or in this case, your products minus your reactants. And so here, if we have our products, we have our 2 NO2s, and again, minus the sum of our 2 NOs plus our O2. And so here, we know the delta H's for all these, and so we just have to really plug them in. And so we have 2 of our NO2s, which again are going to have 33.85 kilojoules per mole. We're going to subtract from it our 2 NOs, which are going to be the 90.4 kilojoules per mole, plus our 1 mole of oxygen at 0 kilojoules per mole. And so all you need to do after that is add up the values, and you have your delta H. It's a horrible delta. Your delta H of reaction with everything in standard state form is going to be -1 or 1131. Sorry. Going to be 113.1 kilojoules per mole. So when you kind of go through and look at all this information, one thing you should just kind of understand here is that this is an exothermic reaction, just stating the fact that when you add 2 moles of NO plus 1 mole of O2 to produce 2 moles of NO2 gas, it's going to release 113.1 kilojoules of energy per 1 mole of the substance.